If you dip a jar of water from a muddy river, you will see bits of mud and sand settling to the bottom of the jar. Where do the mud and sand in the river come from? Since the river is bringing the mud and sand downstream, the logical place to look would be upstream. Here in the high country, the source of the river is a small, swift creek. Mud, sand, and small pieces of rock are being picked up and carried away by the current. But where do mud, sand, and broken rock come from? Look around you. Everywhere you can find things that are slowly crumbling into bits. They are gradually decaying and decomposing from long exposure to the sun, to rain, heat, cold, and wind. They are weathering. In nature, weathering has a similar effect on rock. The rock gradually decomposes. It crumbles into small grains of mud and sand, and gravity pulls them downhill. Eventually, most of the mud and sand is carried into a stream. When rocks freeze and thaw over and over again, cracks develop. Occasionally, a piece of weathered rock breaks loose and gravity pulls it downhill. Tumbled by the current, rocks are further broken and worn into smaller and smaller pieces. All that finally remains of a weathered rock is mud and sand. These bits of decomposed rock are called sediment. Sediment along the banks of a river may remain in one place for many years, but sooner or later the river picks it up again and carries it downstream. When one river joins another, a larger river is formed, and the combined load of sediment is carried away. Eventually, most sediments reach the relatively calm waters of an ocean. The stream's current doesn't extend very far out into the ocean. What happens to the sediments now that there are no longer any strong currents to move them? It's hard to tell here, since whatever happens takes place under the ocean. It will be easier to find out in a man-made reservoir. A stream has been carrying sediments into this reservoir for about 30 years. If the reservoir is emptied, we can find out what happened to the sediments. The sand and pebbles have settled out in nearly horizontal layers. But why? The sediments were carried into the full reservoir by this stream. What happened to them when they reached the calm water? This is a simplified model of a stream flowing into a reservoir. The water running down the canyon represents the normal flow of the stream. As in nature, the stream brings down a mixture of sediments. When the stream enters the still water, the current slows down and the sediments settle out. As the stream shifts its course, the sediments are delivered to a new place. Later, the stream has changed course again. And so it goes. The stream delivers different mixtures of sediments at different times and places, and they accumulate on top of each other. What is the result of this constant change? The sediments have been deposited in layers like those in the reservoir. The sediments that are carried into the calm waters of the oceans behave in a similar way. They settle out in layers in the shallow offshore waters. But the sediments don't always stay in place. This is a sand slide in the ocean off the California coast. Sand that may have started its long trip downhill from mountains hundreds of miles inland is still being pulled downhill by gravity. And there are still other ways that sediments move towards the depths of the oceans. This tank represents a small cross-section of the ocean floor and includes several hills and valleys. The unevenness of the bottom is exaggerated to make the results of the experiment easier to see. Let's watch what happens when we release a fine-grained sediment into the tank. After several hours, the sediment has settled to the bottom and formed a layer. The layer is not quite horizontal because of the exaggerated unevenness of the bottom. Another load of sediment released into the tank will form a second layer atop the first. In the oceans, such a layer may be only an inch or two thick and may extend for many miles. It might lie undisturbed for centuries before another mass of sediment is loosened nearby, perhaps by an earthquake. But then the new flow of sediment will cover the original layers and form a new one on top. In this way, layer after layer of sediment is deposited on the ocean floor. The sediments will first fill in the low places. Once these have been filled in, the layers deposited on top are horizontal, even though the bottom of the tank was not. So it is that when sediments are carried into an ocean, or any body of calm water, they settle out in nearly horizontal layers. These layers resemble the layers of loose sand we found in the reservoir. But this is hard rock. What made it hard? Could the pressure of many tons of rock lying on top have had something to do with it? This is a sample of a natural sandy sediment. Let's see what happens to the sediment when we put it under a hydraulic press and apply 15 tons of pressure. Pressure does help to make hard rocks from loose sediments. But the change is not complete. Something else must be needed to turn sediment into true rock. Let's take a piece of natural sandstone into the lab and examine it. With a diamond saw, a thin slice is cut from the rock. One side of the slice is ground and polished. The slice of rock is then attached to a glass slide. Further polishing grinds the rock down until it's about 1/1000th of an inch thick. Finally, a protective cover glass is mounted on the thin section. We may then study this thin section under a microscope. Polarized light helps reveal the different kinds of particles of which the rock is made. We can see several different kinds of sand grains. But what is the material between the sand grains that seems to be holding them all together? And how did it get there? This irrigation pipe on a Nevada ranch is supplied by underground water from a nearby well. Over the years, the water has deposited a white crust on the pipe. When we drop some acid on the crust, a fast bubbling reaction takes place. This bubbling reaction indicates the presence of calcium carbonate. This rock is in the hills just above the ranch with the crusted pipe. If acid is dropped on the rock, again a bubbling reaction takes place. There must be calcium carbonate in the rock. Could water have deposited calcium carbonate in the rock, as it did on the pipe? A lab demonstration can help answer this question. We'll use some loose sand and cover it with a chemical solution representing calcium carbonate. Let's watch what happens under a microscope. With the time-lapse camera, we can condense an hour into a few seconds. Crystalline material gradually grows in the spaces between the sand grains, cementing them together. This is similar to the way the grains of sand were cemented together in the hard sandstone. Calcium carbonate cement must have been dissolved in underground water that seeped through loose sediments for many centuries, cementing them into rock. Rocks made from sediments are common, and they are always layered. They have been formed from loose sediments which have been pressed and cemented together over long periods of time to form hard sedimentary rocks. In this part of North America, sedimentary rocks make up over 70% of the land. Was all of this rock made from bits and pieces of decomposed rock, or was some of it formed from other kinds of sediments? These are shells of animals that once lived in the sea. Over periods of thousands or millions of years, as these creatures died, their shells collected on the bottom in layers along with other ocean debris. Eventually, the shells and other materials became cemented together to form the sedimentary rock called limestone. This coal mine in West Virginia is deep under the surface of the earth. We don't find any pebbles or seashells in this mine, but sometimes we do find the impression of plant leaves. Normally, leaves and other plant materials that fall into a pond or swamp will settle to the bottom and decay in the stagnant water. But not always. If mud and sand are washed into the swamp, new sedimentary layers will accumulate. When great masses of plant materials are trapped and pressed down by tons and tons of overlying sediments, the plant materials may change into the sedimentary rock called coal. And like other sedimentary rocks, coal is always found in layers. This coal mine is over 1,000 feet under the surface of the earth. Why do we find the impression of a leaf this deep underground? Why do we find seashells high up on a mountainside? And why is rock that was deposited in horizontal layers underwater now tilted high up in the air?